So, we will start a new topic. Now, so far we discussed flow with only velocity field, right. So, it was water flowing or air flowing, but now we will add some more complexity and put a scalar in along with the velocity field. So, what does it mean? We can put ink in flowing water. So, that is scalar, no, the density of ink. So, that will go around with water. So, that is called scalar, which is only magnitude, but it doesn't have a direction. So, we can also have magnetic field in the flow, and that is a vector. So, that is flow with a vector, which I will do later. Okay. So, we will do MHD with that formalism. So, scalar temperature is a scalar, so convection, which we already done. So, I will cover them slightly fast, I mean I do not have time. So, I will do it only the basic ideas I will convey in the lectures. So, let us formulate our equations, and I will work with only real Fourier space, except I will give you the corresponding 4/5 law. We can also derive structure function for scalar fields, and that proof I will not give, but I will state the result. Okay. So, what I will do is flow with a scalar. So, I will just basically put the formalism, then passive scalar turbulence. I will define what passive scalar is. Okay. So, then we will do stably stratified flows like Earth atmosphere is stable, the density is heavy at the bottom and lighter at the top, and then we will work with convection. Okay. So, these are 4 topics I will cover today and tomorrow. So, let us start with scalar turbulence. So, our equations are, so we have a new field. Okay. So, I am going to call as theta, another field theta, which is scalar field. So, it is in the same flow. So, velocity will advect the theta. So, we need to write equation for both velocity field as well as for theta. So, velocity field is the same equation as before, is velocity of the elements of fluid. So, we already done this before, d by dt plus u dot grad u. So, we will assume incompressibility. So, density is constant plus force Fu. So, u subscript means velocity. Now, we have to be careful, there will be 2 forces, one for theta as well as for u, and then viscous term. So, nu grad square u. So, this we have already done. So, I am going to use the results of the past. Of course, we need to, when I say solving scalar equations, then I need to solve both u as well as scalar. Now, what is equation for theta? So, theta is advected with the flow. Okay. So, we will have, so theta is function of x and t or r and t. So, total time derivative of theta. So, I am not going to derive for full thing, but you can derive like what you did for velocity partial. So, you can take a patch of scalar and how it flows with the velocity field. And so, how will this patch of partial move? And it moves, velocity advects it and also changes by diffusion. So, the advection part is this one theta, the diffusion part. So, this must be, so the proof I can only sketch. So, this theta, this part is the theta element, theta total theta inside a small packet, and that can change by advection and by diffusion. So, this is changed by advection, right, the flux, theta flux going out of the sphere, and then we have advection. So, kappa is my diffusivity coefficient. For theta. So, I mean density diffuses, temperature diffuses. So, this is a diffusion coefficient. Okay. And there could be force on this, a scalar force. Okay. So, somebody increases theta, injection, I can inject ink or I can heat the fluid, so that I am supplying temperature thing. So, we keep f theta, it is very useful to keep f theta. Okay. So, this is forcing for theta. The way temperature velocity is forced by stirring it, you can also inject inject theta by, so f theta is positive. It can also be injection at different scales, need not be only large scale. Okay. So, something which changes theta is f theta. Okay. Now, you should not think like force. Force is not necessarily mass times acceleration. So, something which changes it is, I call it force. Some of it is mathematical framework.
F theta and Fu are dependent or independent?
I am coming to that. Okay. So, I am coming to, so that is different types. So, we will do that. Okay. Now, this equation has some interesting properties. So, we can write down equation for theta squared. So, let us write down equation for theta squared. Okay. So, I can multiply this by theta whole equation. So, this will give you d by dt of theta squared by 2. What about the other one? U is still incompressible. Okay. So, I can write this equation, this term is del j uj theta. Yes. Now, I put theta here. So, you can easily show that this del j uj theta squared by 2. Okay, by product rule. So, this is divergence of theta squared by 2 times vector u. Yes. Right hand side will be f theta times theta. So, this is the injection of theta squared, like we have force injection, no, of that gives you increases u squared. Similarly, f theta times theta will increase or decrease theta squared, and the other term is kappa grad square theta times theta. It is like you can do by parts, this part, right. I mean, theta grad square theta can be written as theta grad theta minus grad theta squared surface when I do the volume. Okay. Right now I have not done the volume, so just wait. So, I can now integrate over volume. If I integrate over the whole volume, so there is a whole volume box d by dt of theta squared by 2 integral dr. What about this? What is this for periodic boundary condition? Integral of this 0. With periodic boundary condition, I apply Gauss theorem. So, it will be surface integral. So, left surface, right surface will cancel, top surface, bottom surface will cancel. So, this term gives you 0 by Gauss theorem. Now, right hand side is of course f theta d theta dr plus this one dr. Now, this term is the dissipation term. So, theta squared can be killed, but like of course, ink does not get killed, ink is diffused. So, we use the same analogy as fluid. So, my basically kinetic energy is diffused at some level and it is no more fluid velocity. No? So, you can see that at very small scale we cannot call it fluid velocity, it has gone into thermal heat, heat energy. Similarly, kappa becomes very small, then I do not call coherent motion, I say theta squared has dissipated. Okay. So, this is a dissipation in the same language. Okay. So, this is a dissipation term and the source term. If the source and dissipation are 0, so f theta is 0 and kappa is 0, then what happens to theta squared by 2? Is constant in time. Okay. So, if f theta is 0, kappa is 0, implies integral theta squared by 2 dr is constant. So, this is a conservation of theta squared. So, I am going to call it scalar energy is a generic word which I am going to use for all temperature, density or ink, you know. So, we will call it scalar. It is not energy really, it is a quadratic quantity, but it is convenient to call it scalar energy. So, density square is not same as kinetic energy. Okay. So, this is only for convenience or for mathematical similarity. So, we will call it scalar energy. Okay. So, this is a convention I will follow, fine. So, we can derive some more properties, but this is one property. This will suffice for our thing. Now, what types of flows I will consider in this set of lectures. So, one thing is you can say I focus on scalar, no? So, this actually focus on both, so they are relations. So, one thing is type 1 is passive scalar, where Fu, there is a Fu, but it is independent of theta. That means the scalar does not affect the velocity field. So, that is why it is called passive scalar. So, if there are light dust particles, then it does not do anything to the velocity, it just travels with the velocity field, you know. So, velocity dictates the future of theta, but not vice versa. Theta does not do anything to velocity field. Of course, if particle is heavy, then it will affect the velocity field, but light particles do not. So, you can think of massless particle injected in the velocity field, it does not. In fact, this is used for experiments. So, there are something called tracer particles which are injected inside the velocity field, inside the fluid, and it does not change the velocity field, but it can be used for visualization of the flow. Okay. So, this yes. So, but f theta can be anything, f theta is present, but f theta can be f theta is rather theta is driven by u. So, f theta could also be function of u, okay. But we will assume that f theta is only at large scale, some kind of force which is only at large scale. Okay. So, this is in the class of passive scalar. So, this is called passive scalar, okay. And it is a very important topic for obvious reason that this is used for diffusion of pollutants, you know, or your CO2 or things are, you know, this is most of the time you can treat as passive scalar, at least a lot of physicists work with this passive scalar. Now, second, so Fu is function of theta, but it will, so I am going to make in a stable atmosphere, okay, in this atmosphere. So, density is a scalar for me. No, so by the way, here now density and velocity field are together, right? Fluid is moving, so it has density and velocity field, but because of gravity, so force is rho g. So, rho couples with gravity, okay. Now, this rho g will affect the velocity field, right, because velocity field can be decreased or I mean basically for in the atmosphere gravity I am going to show you that it takes the energy away, kinetic energy away. So, there is a transfer from kinetic energy to potential energy, okay. So, this I will show you, okay, I will prove it. And so, like here the velocity field is function of scalar, so it is not a passive scalar anymore, right. So, we call it also active scalar. So, this is called active scalar, that means the velocity field is affected by theta, active scalar. And this particular example for atmosphere, which is where high density below and low density above, okay. So, for this it is called stably stratified flow, stably stratified flow. Okay. So, this is one class of active scalar where the flow will have property different than Kolmogorov theory. Okay. So, I am going to show you that Kolmogorov theory will not work for this problem. So, we need to modify the spectrum. So, third theory is, in fact, is the same force rho g, but we write in terms of temperature. So, density is inversely proportional to temperature. No, higher, hotter the fluid, lower the density. So, this is minus theta, temperature fluctuation. Okay. So, here it turns out potential energy goes to kinetic, or theta drives the kinetic energy, right. I mean, when you heat the water, kinetic energy is increases by heating. So, or let us say thermal temperature pushes kinetic energy, okay, and this is thermal convection. Okay. So, the difference between these two systems here and here is the energy flow direction. In one of them, kinetic energy is lost to potential, a second potential pushes the kinetic energy, okay, and that changes the physics quite a bit. Okay. So, I will cover these three types of flow in 2 days. Okay. So, let us write down the equation in Fourier space. So, with flux and so on are very conveniently described by Fourier space. So, we write down the equation in Fourier space. So, velocity field is already written, including with f, right. So, f will be fu, so no problem. We need to worry about theta. So, in real space, what was the equation for theta? It was divergence of u theta, right. So, because u is incompressible, so del dot is 0, is that is kappa u square theta plus f theta. So, what happens in Fourier space? So, straightforward, no? You guys are now experts. This one. What about this one? Kappa grad square theta? Kappa k square theta of k. This one? F theta of k. Whatever function is, I just do Fourier transform and I get this. So, we write generically, well, basically f theta of k. This one is a non-linear term, so it becomes convolution. So, in my notes I call it f theta of k, n theta of k, n theta of k is a scalar, okay, it is not a vector. And what is n theta of k? So, divergence will give you I of k dot u of k or what? U of p, or I will call it u of q theta of p convolution sum over p, and what is q? Q is k minus p. Okay. So, this is equation for n theta, or this is form of n theta. You can also write down for theta squared mod theta square. So, theta is complex. Huh? So, what will I do with this to get that? I multiply this by theta star of k, correct, and then add complex conjugate to it. So, resulting equation and add complex conjugate, that will give you theta mod theta square. So, let us write down for with theta star. So, that gives you d by d theta of theta star. So, I will take it to the right hand side. Okay. So, let us take it to the right hand side, this is n theta. So, minus I k dot u q theta p theta star of k, right, and the other term is minus kappa k square mod theta k squared, and third one is the fourth term is f theta of k theta star of k. Add complex conjugate to this. So, this becomes d by dt of mod theta square, theta of k square, right, at cost. So, by product rule. Now, here I will have exactly complex conjugate of this, right. So, it is a real part of this object twice, no, A plus A star is twice real of A, imaginary part cancels. Now, this will become minus 2 kappa k square theta k square plus this is again real part, twice real of this, divide by 2. So, I am doing some derivation just to make you familiar with this, and this I divide by 2 and multiply by 2. So, this is called modal energy, modal scalar energy, modal scalar energy, and I denote it by E of theta k. Okay. Now, there is a minus I sitting here, so I want to get rid of minus I. So, this is real plus I imaginary. So, real of minus I r is 0, right. So, only the imaginary part will contribute, and I squared will give you minus 1. So, minus 1 equals plus. So, it is imaginary of k dot u of q theta p theta star of k, and this is minus 2 kappa k square e theta of k, and this is same as that. So, we just keep it. I am going to call that notation F, the math cal. This is not force, force is English F. Okay. Now, this is math cal F, calligraphic theta of k. So, this is the injection rate. Okay. I am injection rate to theta squared by 2. Okay. Now, this is looks very similar to mode to mode transfer, no. So, instead of u p dot u k star, I have now theta p theta star k. Yes. So, this in fact is very similar, and we can define mode to mode energy transfer from this. Make sense? So, we can do some more work, but I think since I want to bit of speed up, I will write only till here. I mean, you can also define how theta changes the helicity of the velocity field. Okay. Now, all that part I will skip, I will not focus on it, but let us focus on E theta, mode to mode, flux, and what does flux do. So, mode to mode scalar energy transfer, because what about mode to mode kinetic energy transfer? Will it be same or different with when I put ink? What about, so there is a energy transfer from UP to UK. Would you use the same formula which I did before, or will I use different formula? Same. How many if you think same in? How many if you think not same? Or some are uncommitted? Maybe, maybe not, maybe not, right? I mean, so what? How do you derive this mode to mode transfer formula? Is from the nonlinear term, right? U dot grad u term is responsible for energy transfer. Now, for with passive scalar, what is the nonlinear term for the velocity field? It is exactly same nonlinear term, is u dot grad u. Velocity equation does not change. So, the mode to mode transfer for the kinetic energy exactly is exactly the same. Okay. So, Kolmogorov flux, I did not mean say flux is constant, the formula remains the same. Okay. So, let us write that first, because this is important. SUU, so UU means kinetic velocity to velocity. Now, you have to be careful, velocity to velocity. In fact, I kept it in earlier notation as well, UU, U to U. So, K prime, so we had made this vector, no, K prime PQ. So, k prime plus p plus q is 0, but k prime is also minus k. Okay, this we did in great detail. Okay, so in this course, if you remember this formula, I will be very happy. I mean, this is after 1 year, I will ask you, okay, do you remember the mode to mode? So you should remember this. And we derived this is minus imaginary. So k prime dot uq up dot uk prime. So minus k prime is plus k. So if you look at your just slide before, so this minus k prime gives you just k prime, k just k. Okay, so that is, but this is convenient with the k prime. Now this uk prime is uk vector, uk prime is u star of k. Okay, but this is symmetric. So I can change k prime to p and p to k prime. I can follow this. So this is a giver, receiver, and mediator modes, and these are mediator receiver wave number. Okay. Now what do you expect for the scalar now? Now in my book I tried to derive the formula. I derived it, but we will not go through the full derivation, but I will only give the formula. Okay. So here we have the velocity field which is blue. So these are velocity field blue. Okay. So these transfers are UU transfers, which is I already wrote. But green are the scalar fields. Now if you look at what I wrote in the previous slide, energy equation for scalar. So let us write the equation for the energy. It has d by dt of E theta of k is sum p. So I have k dot uq theta p theta star of k. Okay. So let us turn off the viscosity and diffusivity and force f theta, they are off. So this is the term. Now if you focus on a single triad, this one, then what will I get? So this sum will become only 2 terms. Now I am going to make a change of notation here. Okay. So k prime is minus k. So this is a minus k prime and this was k prime. Okay. Star becomes that. Now since it is a sum, so I will have one more term minus k prime dot up theta q theta k prime. So these are only 2 terms. Now E theta of k can change by scalar energy transfer from p to k, or actually we have it here. So k is getting from q and from p, right, both the sources. Now among these the sum is given to me, but I have to identify which way is coming from q and which is coming from p. Now one physical argument which I gave in the class before is the candidate, this is p to k prime. Why? Because if I look at my energy in real space, so it is u dot grad theta, these are dynamics part, the advection part, I multiply this by theta. So what does u do? U only advects. I mean u is a different category, u is not participating in transfers of theta and theta. So this must be the mediator, no? Yes or no? This in fact is different category, different vector field, different field. This is a receiver, right, because it is coming into this. This is my n theta, this is a giver, because I wrote d by dt of theta and multiply with theta. I said this is my receiver and this is a giver. Okay, so this is a good interpretation. So since this is a mediator, so the gradient acts on u. So k prime dot, this is a mediator uq, the one multiplying k prime, and this is my receiver, and I am saying p is a giver, so this must be the giver. So, this is giver and receiver, and this guy u must be mediator. Now, there are two of them, but this is a p giving. So, this can't be the mediator u p. Theta p is the mediator, theta p is the giver. If I say p to, so I am fixing it here, okay. I am interested in this one, S theta theta. So, I have it in my next slide, next click. So, S theta theta p to k prime. If I am looking for it, then this must be the giver and this must be the receiver, and u, because theta theta are exchange, and the u q must be the mediator. So, this is what I have it here, okay. So, this is a mode to mode scalar energy transfer in a triad, mode to mode, okay, and using this I can now define flux, right. So, this is just set of, so this physical argument. We can also construct mathematical argument very similar to what we did for, well, I did not do in great detail, but we can construct mathematical argument as well as from tensor algebra, okay. Are you happy with this? So, this is a mode to mode energy transfer, giver is here, receiver and mediator. So, mediator is velocity field and that dots with receiver wave number. Okay, and there is a minus sign, because you see there is a minus sign here. Now, once I know mode to mode energy transfer, I can define flux. So, what is the flux? So, flux is theta squared coming out from the modes inside the sphere to the modes outside the sphere. That is the definition. It is a scalar quantity, is not like a vector quantity of, it is a multi-scale energy transfer. Okay. So, the modes inside giving mode to modes outside. So, P is here, K prime must be outside, and Q will be of course there, because without Q transfer cannot take place. Though it is mode to mode, the mediator is important, mediator must be present, otherwise no transfer. Okay. So, but I know the formula S theta K prime P Q vectors. So, I need a sum, right. So, this we call it pi theta of radius of the sphere K naught. So, P must be inside. So, P is less than K naught, less than equal to K naught, receiver is outside, K prime greater than K naught. Okay. So, this will give you the flux, and you can compute it by pseudo-spectral method, okay, by Fourier transform you can do it. Now, we can also define shell to shell transfer, which I will not use for this lecture, but we can also define. So, we can make two shells like this, another shell which is bigger, shell M to shell N. So, imagine I want energy transfer from shell M to shell N. Now, only scalar energy transfer. We already done UU transfer. UU transfer will be exactly same what we did before, because nonlinear term is exactly the same for velocity field. So, theta field scalar energy transfer will be, so the notation is theta comma M. So, this is the M is giver. So, M is superscript above, and receiver is theta comma N equal to, no, I do not call it S, I call it T. Okay. So, this shell to shell transfer, shell M to shell N. So, from top to bottom, this is the notation which we follow, and these again two sums, S theta theta K prime P Q. So, K prime belongs to receiver is N and giver is M. Okay. So, straightforward, we can do variable energy flux. In fact, this is important concept which ties up convection, scalar, passive scalar and stably stratified flows. Okay. So, this is the my combination point, this is a meeting point. So, we derived for kinetic energy, So, a flux in a shell, or sorry, energy in a shell can change by what? There is a flux like this coming out. So, this is called inner flux pi. So, I am maybe I will try to improve this. So, let us make these two circles bit better. Okay, two potatoes. Now, I am looking at scalar energy of the shell. Okay, how does it change? So, d by dt is very similar like what we did for velocity field, E theta of k. I should multiply by delta k, no. So, this is the energy change in the thing, but I will divide by delta k everywhere. So, it can change by change in the flux. So, this is pi k plus dk, this is pi k. So, what comes in is pi k, what goes out is pi k minus k. So, this will be equal to pi k minus pi k plus dk, correct. So, in is plus, right, that is a notation that will increase E k. It can also change by external force. If I inject, then I can change. So, this is f theta of k, math scale, and it can decrease by dissipation. So, this is plus f theta of k times delta k minus d theta of k delta k. Delta k and dk are same for me, okay. Is that clear? So, this straightforward from energy. Now, divide by delta k everywhere, and that will give me the equation d by dt of E theta of k is minus d pi by dk. Why minus sign? Because this is a k plus dk with a minus sign, plus f theta, so pi theta, okay, pi theta, plus f theta of k minus d theta of k. Remember this? This was exactly same for velocity field, except u was replaced by theta. Now, what happens under steady state? Steady state, so this goes to 0. So, and is only function of k now. So, I use total derivative. So, d pi theta by dk is f theta of k minus d theta of k. Okay. So, but I want to emphasize it because I am going to use it for my later lectures. So, this is my equation for how flux will change with k. Now, there are various scenarios. So, let us imagine that we focus on inertial range. In the inertial range, my d theta also will be negligible. It is there, but it is small compared to f theta. Okay. Kolmogorov theory assumes f theta to be 0 in the inertial range. Okay. So, there are now various scenarios. So, that is in my next slide. So, these were, so you see this f theta is a green one. Okay. Now, here f theta is 0, f theta comma in, in is inertial. So, it is slightly tiny for you, but this is f theta injection rate in the inertial range. It is 0. So, what happens to the flux? So, we have, remember now this previous slide, d theta is f theta inertial, d theta I am ignoring. If this is 0, then what happens to f pi theta? Constant. Now, constant can be two constants, one is 0 or one is non-zero. We will assume it to be positive, it goes from large scale to small scale. So, this is 0, it is the equilibrium theory, which I mentioned that all these modes are kind of sleepy, they do not give any energy to each other or very little energy, and they are all equal energy. It is like thermodynamics. Okay, that is the analogy I had discussed. So, equilibrium corresponds to thermodynamics. It is uninteresting for our set of lectures, and I expect this to be k squared. I have not seen papers discussing this, but I have not really looked in literature, but passive scalar with pi theta being 0, which will be there if you make kappa is 0. Okay. So, this is what something which you should try. So, Anando has some data also. So, we have quite a bit of data. So, we could try to see whether we get k squared in 3D for theta squared as well. Remember, every mode if has same energy, then the shell spectrum must be k squared, right, because area of shell is k squared. So, the prediction is E theta of k is k squared for equilibrium scenario. Okay. Now, this is one scenario which follows from variable energy flux, which is I like it very beautifully. Okay. I mean, this is now if it is positive and constant, then here this is a passive scalar regime, constant flux. So, I will do it today. So, I hope you will give me the time. So, passive scalar I will derive the spectrum for passive scalar. If constant flux, the derivation is very similar to what is for Kolmogorov theory for hydro, and it works nicely. You get 5/3 for theta spectrum, but I will derive it. Okay. So this passive scalar turbulence, we call it passive scalar turbulence, because nonlinearity must be strong. So, otherwise there won't be cascade. Now, this one is pi theta is negative mod f theta of in. So, my forcing is sucking the energy out, kinetic energy, whether we are talking about, well, we are talking about not kinetic energy, we are talking about theta energy. Yeah? So, this is something which I will not probably use it in the same language, but you see we can also define for how pi theta changes with k. So, if it is there, then pi theta will decrease, right, I mean clearly, because this is negative. So, pi theta will decrease. For the scalar, theta is the flux of theta, pi theta, flux of theta should decrease, and if it is positive, then flux must increase. Okay. But please remember, this is for pi theta, it is not pi u. So, to determine pi u, I have to replace this force injection by Fu. Okay. So, this can be concluded. I am going to use only this one for passive scalar, this one, but I will not use these two in my set of lectures. Okay. But I will use Fu. So, Bharat, you have some question?
After k dissipation, we have assumed the same type of nonlinear behavior.
You mean in this range?
Yeah, as related to.
No, this where I have to include d theta as well.
Yeah, so after that we have assumed the same sort of nonlinear behavior that we were had in.
Yes. So this part I will not derive it here in my this thing, but you can apply maybe Pau kind of model. Okay. So this part I will not do it, but I have some discussion in my book, but we can discuss it privately. Okay. But this d theta has to be modeled. Okay. And this where pi theta increases because my injection is positive. So it depends on how this external force on theta is injecting theta squared. Is it positive, negative, or 0? Okay. In fact, this is passive scalar. This is, well, no, I will not connect it. For Fu, I know, well, I can also talk about f theta, but I will not use it right now. For Fu, I know the signs, but we will do it. So this is, no, I will not say anything. So this is for pi theta. Okay. And of course, Fu also has variable energy flux, same diagram which we did before. So, I am going to use Fu formulas for my future discussion, except for passive scalar we will use this. Okay. So, we stop. Thank you.